So we are going to go ahead and jump into today's material on intermolecular forces. As a quick reminder, what we went through yesterday, we talked about the different types of solids, covalent network solids, giant macro molecules like diamond and glass, where the molecule, the whole thing, the big crystal you hold in your hand, is held together by covalent bonds. Similarly, when you have an ionic crystal, like a giant salt crystal or some large crystal like that, it's held together with ionic bonds. These ionic and covalent bonds are similar in strength, and they are generally much, much stronger than the intermolecular forces or bonds that we're going to talk about today that we see in molecular solids, where we have individual molecules, the water molecule here, which internally has covalent bonds, but between the water molecules are these inter means between, the intermolecular forces. Okay? So, today is really about looking at and learning the names and the strengths of different types of intermolecular forces and how they change the properties of the material. Why some substances are solids, liquids, or gases at given conditions, and things like what other properties will be affected by the strengths of these intermolecular forces. All right? So, step one, there are two big categories of intermolecular forces. And those categories are driven by whether the molecule is polar or not. If a molecule is polar, that means it has a permanent positive end and negative end. We've talked about this. You should be able to, at this point, look at the structure of a molecule like a Lewis structure and determine whether a molecule is polar or non-polar. We spent a bunch of time doing that. Obviously, it's going to be critically important for this unit that you bring back that kind of ability to look at Lewis structures, to look at molecules, and determine whether they're polar or non-polar. As a reminder, the big thing is the molecule asymmetrical? Is it asymmetric with polar bonds? That's what we're looking for. And we will talk about that a little bit when we get into some examples later on. But if we have polar molecules, so if we pass that first criteria, it's polar. That means that the positive and negative ends attract and repel each other. We're particularly interested in these attractive forces, the positive end of one molecule attracting the negative end of another. That is an intermolecular force, which can sometimes be called an intermolecular bond, as we'll see in a few minutes. So this intermolecular force, which exists between these polar molecules, is known as a dipole-dipole interaction. That's the term, the name that you are expected to know. Dipole, remember that means a molecule with two poles, di meaning two, and it's the positive pole and the negative pole. So this attraction, positive to negative, in these permanent polar or dipole molecules is called a dipole-dipole interaction. Okay? So if you were asked, what type of intermolecular force does this generic polar molecule have? You would need to say dipole-dipole interaction or dipole-dipole force or dipole-dipole. That's what they're looking for as an answer to a question. That question will, with 100% certainty, be on our test, and it will almost surely be on the AP test. These are very common questions on the AP test. Now, some molecules, ones that are very polar, have particularly strong dipole-dipole interactions. And the dipole-dipole interaction has a range of strengths depending on the polarity of the molecule. The more polar the molecule is, the stronger this interaction will become. We, as chemists, give very strong dipole-dipole interactions that form under certain circumstances a special name. We call them hydrogen bonds. Okay? Now, it is very important to understand that these hydrogen bonds are still much weaker than covalent or ionic bonds. All right? Covalent and ionic bonds are up here. Hydrogen bonds are down here. Much weaker. All right? But compared to dipole-dipole, they can be significantly stronger than a dipole-dipole interaction. So the question that you need to be able to answer, the things you need to know about them, is you got to understand under what conditions do we consider a dipole-dipole interaction a hydrogen bond. This happens in a polar molecule when we have sort of two conditions are met. Number one, you have a hydrogen atom covalently bonded to a fluorine, an oxygen, or a nitrogen. You must have a hydrogen atom covalently bonded to fluorine, oxygen, or nitrogen. There's some wiggle room here in some weird esoteric cases that you will never see on the AP test or in a first-year chemistry class. Okay? But there are some interesting research articles about maybe sulfur can do some of this and some other things like that. Anyway, don't worry about it. Hydrogen covalently bonded to fluorine, oxygen, or nitrogen. When you have that, this bond is extremely polar because hydrogen only has one electron. Fluorine, oxygen, nitrogen are the three most electronegative elements on the periodic table. They pull that one electron away from the hydrogen strongly. That electron spends most of its time around the oxygen, the nitrogen, or the fluorine, which means that we have sort of a naked proton out here. And that gives us a very strong positive charge. All right? So, what that means is that if this very strongly positive hydrogen is exposed or can interact with a fluorine, oxygen, or nitrogen primarily, but sometimes other substances, then you get this particularly strong intermolecular force, this particularly strong dipole-dipole interaction that we call a hydrogen bond. Notice it is an interaction between two separate molecules. This is not the hydrogen bond. Yes, it is a hydrogen-oxygen covalent bond, but it is not what we mean when we say hydrogen bond. Hydrogen bond refers to this very specific between molecule force that exists when we have these very polar molecules. So this does not have to have, this oxygen here doesn't have to have a hydrogen bonded to it. It could just be usually a fluorine, an oxygen, or a nitrogen in another molecule. And that is a question that has come up on the AP test a couple of times in the recent past. We will see some examples of that when we start to look at AP style test questions. Question. Yes. So how do I know if this is a covalent or ionic bond? The simple test is if it has a metal in it, it's ionic. So if you have metal and non-metal, that's ionic. That's a large difference in electronegativity, transfer of electrons, ionic bond. To be covalent, it's non-metal, non-metal. Smaller difference in electronegativity means that they share electrons. So that's our big, category distinction between ionic and covalent. So the hydrogen bond, once again, forms when you have a polar molecule where you have two criteria. One, this has to have a hydrogen covalently bonded to a fluorine, oxygen, or nitrogen. And then the other molecule has to have generally a fluorine, an oxygen, or a nitrogen that the positives and negatives can interact. Yeah. So yes, the solid lines indicate covalent bonds. This is one molecule covalently bonded together. Here is a second water molecule. These water molecules are separate, but attract each other using hydrogen bonds. Hydrogen bonds, once again, are just a particularly strong form of dipole-dipole. They are nowhere near as strong as covalent bonds. So when you go into biology next year, and they start talking about hydrogen bonds, which are super important in biology, I do not want to hear any biology teachers coming back and say, why do your kids think that hydrogen bonds are as strong as covalent bonds? They are not. Okay? And I am recording this, and I will play it back to you if those biology teachers come to me and say that you're trying to say that. Hydrogen bonds are much weaker than covalent bonds. They are simply the strongest, generally, of the intermolecular forces. All right? Okay. We've now done 2 of the 3 intermolecular forces. Dipole exists in polar molecules that are just sort of normally polar. Hydrogen bonds exist in special, super strong polarity. Okay? Much weaker than covalent, but strongest of the intermolecular forces. The third category exists in every type of substance. So the third category of intermolecular forces exists in every atom, every molecule, every substance. Now, because non-polar molecules do not have any of these dipoles, these are the only forces that exist in non-polar molecules. They are known as London dispersion or just dispersion forces, and they are a temporary dipole. If you have an atom with a distribution of electrons, it can happen that the electrons randomly are unevenly distributed, giving us a negative end and a positive end in our atom or molecule, just due to random chance. When that happens, the atom can affect the atoms around it, causing a cascade of positive-negative interactions to take place. But because this positive and negative interaction is driven by just random movement of electrons, they can come and go very quickly. So, London dispersion forces are temporary dipole forces that are caused by the random movement of electrons. The reason that they exist in every substance has to do with the fact that they are caused by random movement of the electrons, and every substance has electrons that are moving around. London dispersion forces are the only type of intermolecular forces that exist in non-polar molecules. They also exist in polar molecules. The relative strength of the London dispersion forces and our dipole forces depends on primarily the number of electrons. Atoms or molecules that have a large number of electrons can have strong or will have stronger and can be very strong London dispersion forces. Okay? Frequent questions on the test, AP test and my test, therefore, that talk about these ask you to do a couple of things. They may give you molecules that are relatively similar, some non-polar, some polar, some with hydrogen bonding, and ask you to identify which ones will have the strongest intermolecular forces. Okay? They may give you some molecules and tell you which one has the strongest intermolecular force and ask you to explain why. Those are the big types of questions. What we're looking for in these problems is we're looking for clues as to which molecule has the higher intermolecular forces, and then we want to look at its structure and identify what types and why they might be strong or weak. Okay? Now, the main thing is that it is not simply looking at the structure that gives us or tells us what's going on. Because these intermolecular forces also explain lots of properties of different molecules. And the AP test frequently gives us information about these different properties and asks us to use it to justify our reasoning. Anytime you're reading a question and it says justify is a keyword on the AP test. That means use the data from this problem in your explanation. If they say explain, if they use the explain word, that means you can use your general knowledge. But justify has a particular meaning, and that means use the data that came in the problem. It's possible that the data they're going to talk about are properties of molecules that are intimately related to the strength of the intermolecular forces. And so we're going to look at a couple of different examples. Number one, the vapor pressure. Okay? Vapor pressure is something we have talked about before. We talked about it a little bit when we were doing gases. Remember, we talked about the water vapor pressure. And that was how much water would evaporate in a closed container. So I want to go a little deeper on this vapor pressure right now. I start off with an empty container. Okay, so imagine I have this glass bulb with mercury inside here and it's empty. I inject some liquid into this glass bulb. Okay, that liquid begins to evaporate. So I have gas particles that are leaving the liquid state. They're evaporating and turning into a gas. That gas builds up inside this bulb, creating some pressure inside here. As the number of gas particles builds up inside here, some of the gas particles hit the surface of the liquid and condense. So now I've got a process where I've got gas particles leaving the liquid and gas particles coming back. At some point, the number of gas particles leaving and the number of gas particles coming back balance out. And the liquid stops functionally, like the amount of liquid stops changing. Here, I'm losing liquid. Liquid's turning into a gas. The amount of liquid is decreasing. Here, the amount of liquid is stable. We reached a balance between the particles leaving and the particles coming back. If I measure the gas pressure inside here, that is the vapor pressure. What pressure of vapor is required to balance the rate of particles leaving and rate of particles coming back? The vapor pressure is going to depend on two key factors. It's going to depend on the temperature, which tells me how much energy the particles in the liquid have. But it's also critical for this unit, going to depend on the strength of the intermolecular forces. If the intermolecular forces are strong, hydrogen bonding, large dipole forces, a very strong London dispersion force, if those forces are strong, it's harder for the liquid molecules to break away. If it's hard for the liquid molecules to turn into a gas, fewer of them will. That will lower the vapor pressure. So a low vapor pressure means strong intermolecular forces. All right? This is very important to understand. It's a very frequent way for them to look at and tell you information about the strength of the intermolecular forces. The higher the vapor pressure, the weaker the intermolecular force. It's easy for the liquid to turn into a gas. All right? Let's look at an example, okay? Here, I'm going to show you a video. This has two different substances, okay? We have hexane and pentane, and we're going to measure their vapor pressures. Let's see. All right, so first, we got hexane in this bulb. Again, it's empty. We inject some liquid. It evaporates, and you can see it's pushing the mercury up as it evaporates, okay? So hexane. Then pentane. Pentane's next. Do the same thing with pentane. They injected the exact same amount of liquid in both cases, okay? This difference here is driven by the vapor pressure. Which of these two substances has a higher vapor pressure? Think about it for a sec. Which of these two substances has a higher vapor pressure? Think about that for a sec. Check in with your neighbor. Check in with somebody you're talking to. Which one's got the higher vapor pressure? You can turn around and talk to somebody behind you. So Which one has a higher vapor pressure? Pentane. It has pushed the mercury further, right? This is the difference in vapor pressure. Now, question 2. Which one has stronger intermolecular forces? Think about it. Don't say anything. Think about it. So which one has stronger intermolecular forces? Again, check with your neighbor, talk to your partner. Which one has stronger intermolecular forces? All right. So remember what we said. High vapor pressure, weak intermolecular forces. Hexane has higher intermolecular forces, and we know that because it has a lower vapor pressure. Now, let's take that next step. Which one of them, or now we want to explain why based on their structures, based on what molecules they are. Hex means 6, and the ane means just hydrogens, right? This is way back to the beginning of the course. 6 carbons with hydrogens. Pent means 5. Pentagon, 5 carbons, C5H12. Pentane is a smaller molecule. It has fewer atoms. That means it has fewer electrons. Both hexane and pentane are alkanes or hydrocarbons. They are non-polar. Remember our unit where we did our liquid chromatography? If it's just carbons and hydrogens, that's essentially non-polar. So these are both non-polar, which means no dipole-dipole interactions. It's only London dispersion forces. So if I asked you to identify what types of intermolecular forces, you would say London dispersion forces, London dispersion forces. The London dispersion forces of hexane are stronger. We know that because it has a lower vapor pressure. The reason why they are stronger is that hexane has more electrons. It's got an extra carbon, that's 6 electrons, and 2 extra hydrogens, that's 2 more. So it's got 8 more electrons than the pentane does. There are also effects in here having to do with the size of the molecule and other things like that, but that's a little trickier and generally less important. The most important part here is the number of electrons. The number of electrons is the main driver for London dispersion force strength. Question. So if you draw out the Lewis structure, the ane ending tells us that you're going to have the carbons all in a row, no double bonds or anything like that. So if you draw the carbons out, each carbon in the middle has to have 2 hydrogens, and the ones at the end have to have 3. It's the only way you can do a Lewis structure. In general, they'll give you the chemical formulas. Now, vapor pressure also strongly correlates to melting points and boiling points. We're going to talk more about that tomorrow. But melting and boiling points correlate directly to the vapor pressure. Okay? When substances have low vapor pressures, then their melting and boiling points will be high. And that makes sense. If the intermolecular force is strong, it takes more energy to pull those molecules apart to change their phase. We'll talk a lot more about that tomorrow. Question? So the vapor pressure, again, is caused by the liquid turning into a gas. To do that, the liquid molecules have to come away from each other. They have to move apart. If they attract each other strongly, it's hard to do that. And fewer liquid molecules will change into a gas. So the vapor pressure will be lower. So the stronger the intermolecular force, the lower the vapor pressure will be. Now, there are several different types of things. Melting and boiling points are one that we'll talk about more tomorrow. But I also wanted to show you and talk about another property, the viscosity of a liquid. Viscosity is a measure of fluid flow, how well a liquid or fluid will move, okay? Its resistance to changing shape, the resistance to flow. High viscosity means that the substance does not flow. Honey has a higher viscosity than water, okay? Water flows very easily. Honey is thick and viscous, all right? So, it's a great word. What I have, this video, is some more hydrocarbons. These are oils, so relatively long chain hydrocarbons. They're all non-polar, okay? Let's go ahead. I'll show you this video of the viscosity of different liquids. You guys can't hear it, but the music they're playing is Firefly. It's really good. These are all different motor oils. Also, it's in Spanish, but whatever. All right. So let's talk about it. These are different oils. The main driver of the difference in the viscosity is how long the chains are. Because larger molecules why do they have higher viscosity? What's the difference between a larger molecule and a smaller molecule? More bonds, yes. What did we say is the driver for London dispersion forces? What's the number one most? The electrons. The larger the molecule, the more electrons it has. The higher the London dispersion force, the higher the viscosity. Okay? Strong intermolecular force doesn't flow well. Okay? Viscosity also has more to do with the shape of the molecule. Long, stringy molecules can stick together better than small molecules, which can slide around each other easier. So viscosity is not quite as clean a property, but it is one that they have referenced at least once in the last 10 years of AP tests. So, yeah, I can play it again. But here's the idea. Low viscosity flows well, weaker intermolecular forces. Higher viscosity, strong intermolecular forces does not flow as well. Okay, doesn't flow as well. All right, you want to watch it one more time? No, I mean, that's it. Yeah, this is the end of the video, but it will take quite a while. Sort of the most you can watch. There's a camera from a science institute in Australia, I think, which has pitch, and several different substances are actually liquids with flow rates that are just very, very low, very extremely high viscosity. And there's one that does like a drop every couple of 100 years. They have a camera that can watch it, and they've been running the experiment since like the early 1800s or something like that. Something like that. They weren't filming back then, but they did start the experiment back then. So, yeah. All right. So, remember, strength of intermolecular force affects the properties. To identify the intermolecular forces, you have to identify whether the molecule is polar or non-polar. If it is polar, it's going to have either dipole-dipole or in special cases, hydrogen bonds, every molecule, every atom, everything has London dispersion forces. London dispersion forces, however, are the only forces that are in nonpolar molecules. However, London dispersion forces can be stronger than dipole-dipole or hydrogen bonding given enough electrons in the molecule. Question? It's in two, yes. So if a problem said, hey, here's a polar molecule, what type of intermolecular forces does it have? You would have to list both. You have to list dipole-dipole and London dispersion forces. No. You have to, if they say what name the force is, they want both of them. If it's a hydrogen bonding molecule, you can say hydrogen bonding and London dispersion forces. You don't need to say hydrogen bonding and dipole-dipole, although that might be true. They don't, all the questions we've seen, hydrogen bonding plus London dispersion is good enough. Yes, you always write London dispersion force. And then the question is, do you add dipole-dipole? Do you add hydrogen bonding? Okay, let's look at an example. So, take a look. We have a question here. Which of the following would you expect to have a higher vapor pressure and why? Don't answer now. I want you on your notes to write down which one, okay, and why you think it's true. Question. So we're not going to answer yet. 2 or 3 minutes, couple of minutes, look at this question, talk to your neighbor. We'll come back and go over it. Grab a seat, listen up. Here we go. Step 1. You need to identify what intermolecular forces are present. That means you have to figure out if the molecule is polar or nonpolar. So I look at the molecule. Is it symmetric? Yes, absolutely symmetric. CCl4. Sure, the bonds are polar. Chlorine is more electronegative than carbon, but it is an even symmetric tetrahedral molecule. Non-polar. Methane, CH4, same thing. Carbon's more electronegative than hydrogen, but this is symmetric tetrahedral molecule. Non-polar. These are both non-polar. What type of intermolecular forces are there in non-polar molecules? No, I'm asking what type? What type? What type? London dispersion forces. So if I asked you what type of intermolecular forces are present in these molecules, you need to be able to answer London dispersion forces. And that's it, because they're nonpolar. You have to look at the symmetry of the molecule. Symmetry of the molecule. It's funny because I just said that like 5 times. So, all right. Now, we are trying to judge which of them is stronger. So, what determines the strength of a London dispersion force in a molecule? The amount of electrons. Which of these molecules has more electrons? CCl4, many more electrons. Each chlorine has 16 more electrons than the hydrogen. So, CCl4 has the stronger intermolecular forces. What does that tell me about its vapor pressure? A lower vapor pressure. The stronger the intermolecular force, the harder it is for the liquid to turn into a gas, and the lower the vapor pressure will be. So methane has a higher vapor pressure because it has weaker intermolecular forces. In this case, because it has fewer electrons. All right, one more example. The vapor pressure of CBr4, carbon tetrabromide, is lower than the vapor pressure of HBr, okay, hydrogen bromide. Why? So this is a question that's asking you to explain why. I'm not going to ask you to answer right now. I want everybody to have a chance to think and talk about it. Remember, you got to think about what types of intermolecular forces there are and the strength of those intermolecular forces. All right? So again, let's take 3 or 4 minutes. Think about each of these molecules. You want to identify what types of intermolecular forces, and then you want to talk about and think about the strength of those forces. All right? All right. Let's go through it. To answer the why, to explain what's going on, we need to identify what types of intermolecular forces are present. Then we need to justify, to explain, I should say, why one of them is stronger than the other. So, step one, I have to look at the molecule and figure out if it's polar or non-polar, because that's going to tell me what types of intermolecular forces. Carbon tetrabromide. Is it functionally the same as carbon tetrachloride? It's a symmetric, non-polar molecule, which has only London dispersion forces. So only London dispersion forces. Hydrogen bromide is polar, right? Hydrogen bromide is polar. It has London dispersion forces, sure, absolutely, everything does. Does it have hydrogen bonding? No. Hydrogen bonding is fluorine, oxygen, nitrogen. Bromine is not fluorine, oxygen, or nitrogen. So it has dipole-dipole interactions and London dispersion forces. But the problem tells us that carbon tetrabromide has a lower vapor pressure. That means carbon tetrabromide has stronger intermolecular forces. How can only London dispersion force be stronger than London dispersion force plus hydrogen or plus dipole-dipole? The amount of electrons. Carbon tetrabromide has way more electrons, which means its London dispersion force is stronger than the London dispersion force plus dipole-dipole of the hydrogen bromide. This is a common question that comes up on the AP test, where they ask you, they tell you which one is stronger, and they expect you to explain why based on the properties that we've been talking about. Okay? All right, that's it for intermolecular forces. Question? Yeah, that's not a question that it's complicated. So you will not be asked to judge that kind of question. The way that we see these is either the molecules all have basically the same number of electrons, plus or minus 1 or 2 electrons is not generally a big deal. So they'll give you ones with all the same electrons, but different hydrogen bonding, dipole-dipole, like that. Or it will be very clear one of them has way more electrons than the other, making the London dispersion forces really strong. They're not going to ask you these fine distinctions. There's no easy way for you to do that. Question? Like the first question I did up here? Not in this situation. The only time you might have to do that is if the molecules basically have all the same number of electrons, but one of them has hydrogen bonding, one dipole-dipole, and one is nonpolar. But they have the same number of electrons. We'll see some examples later on. All right, that's it. That's it for this lecture. You got 10 minutes to work on the Chem 101 assignment. There is a Chem 101 to work on. Pull that out and get started.